Today's sixth Samvaad-Talk by Professor Ashok, and again we are in the realm of basic sciences, so into basic physics as yet. So his talk is on the dynamics of soft matter. Is it dynamics and soft matter? Okay. So it looks to be very interesting to draw parallels between bubble oscillators and living systems and the physics behind. Let me hand over the mic to Professor Subir Roy, who has agreed to chair the session.
I have the pleasure of introducing Professor B Ashok. He doesn't need an introduction, though he has been our colleague for a long time. But nevertheless, we have to do the due processes. So Dr. B Ashok received his PhD in physics from University of Massachusetts, Amherst, specializing in theoretical polymer physics. Following postdoctoral stints at Lorentz Institute of Theoretical Physics, Leiden in Belgium. In Netherlands, right? Yeah, sorry. Yeah. And Material Science, Materials Research Center, IIIT-Bangalore. He was a faculty member at the Advanced Center for Research in High Energy Materials, Hyderabad Central University for some years, before joining IIIT-Bangalore, where he is currently an associate professor. His principal areas of research interest currently include soft matter and polymer physics, topics in dynamical systems theory, such as neuronal dynamics, biomechanics and complex fluids, and bubble dynamics and cavitation. His PhD title was on dynamics of electrolyte solutions and diblock copolymer in an electric field, which he did with Professor Muthu. Forget the name. And this gentleman gave a wonderful talk 4 years back, which I still remember vividly. And the talk was on menagerie of viruses, organizing principles of virus assembly. So he comes from a very distinguished group of researchers from the University of Massachusetts, Amherst, and I'm sure his talk will be just as interesting as his supervisor's talk was.
As you can see, the title of today's talk is on dynamics and soft matter physics, and I'm going to concentrate especially on bubble oscillators and also some work we are doing which is relevant to living systems, and by and by you'll see what I'm talking about. So essentially the work that I'm doing in complex system soft matter physics spans these topics: bubble dynamics and acoustic cavitation, which is what I'm going to concentrate on today for most of the time. Then some work on dynamics of vesicular nanotubulation, when you pull at a vesicle, which is a phospholipid bag of micrometer dimensions, a nanotubulation occurs, a tube is pulled out. I'll tell you about the dynamics of that. And other topics we have been looking at are, as you can see, polymetric systems, physics of living systems, critical behavior and optimization problem, which is one area which has some overlap with some of the people here. That was looking at how to optimize the traveling salesman problem. Then some work on aspects of climate modeling, especially tropical precipitation. Then also some other work we are doing on synchronization in biological systems, including neuron dynamics, and how do you model things like taste and smell. Okay. But as I said, I'm going to concentrate on the first two topics for most of the talk. So when I say dynamics, what exactly do I mean? What we mean by dynamics essentially is the time evolution of a system. So when we look at behavior of systems in day-to-day life, most of these systems are nonlinear in nature. Of course, when we describe them, we make a linear approximation to make analysis to be easier and to simplify life. But in general, when we talk of dynamics, we are essentially talking of nonlinear systems. So what exactly do we mean by a nonlinear system? How is it different from a linear system? So when we talk of a linear system, essentially a linear superposition is obeyed in the sense that a function of several variables is equal to the sum of the functions of the individual variables essentially. So f of x1 plus x2 and so on is equal to the sum of the individual functions. So superposition, on the other hand, this principle is not obeyed by nonlinear systems. That's the distinguishing identification between them. And when we talk of dynamical systems theory, essentially it's to provide us with techniques and tools in order to study complex systems which are for the large part nonlinear. And also when we talk of dynamical behavior, in general we talk of either the oscillatory regime, which is what is well-behaved regime, and moreover, the other interesting regime is the chaotic regime, where even small changes in the initial conditions will take you far off from where you were earlier. So essentially, again, I'm repeating myself. Superposition principle is obeyed by linear systems, as you can see. And when you talk, for example, if you talk of linear waves, the amplitudes simply add up. Examples of these in everyday life are electromagnetic waves, Maxwell's equations, small amplitude acoustic waves, and Schrodinger's equation. Linear circuit theory analysis all obey linear superposition principle. And as I just said, it's not obeyed by nonlinear systems. Amplitudes simply do not add up when you are talking of a nonlinear wave. A simple example would be the square of two quantities. Obviously, it's not equal to the sum of their squares, right? It's not superposition doesn't hold. Similarly, when you talk of trigonometric functions, sine of a plus b is not equal to sine a plus sine b on the whole. And typical examples of these are seismic waves, what you see in earthquakes and all, water waves, tsunamis, things like that, large amplitude acoustic waves, sound pressure waves, chemical waves, when you have interacting solutions of chemicals interacting in a beaker. Incidentally, these give rise to very nice pattern formation, which are known as Jabotinsky patterns. Then you have gravitational waves, which are in the news recently. All these are nonlinear waves. Okay, so briefly, for large part, I'll be giving a historic background because many of you might not be aware of this area. So broadly, the field of nonlinear dynamics or chaotic behavior started with Henri Poincaré back in 1898. And he was motivated by the desire to know whether the solar system is in a stable configuration or not, whether the planets would fly off or would they remain as such. So now the problem with the solar system is you have more than two bodies, the three-body problem. Whenever you have three bodies, you cannot have a closed form equation describing the system. So for example, when you have three bodies, which might be the sun, moon, and the earth, each is acting on the other. So the best solution to the motion of these three objects that you can obtain is a numerical solution, and that you'll have to occasionally update as and when you have slight perturbations coming in. And Poincaré was the first to think of the possibility of a chaotic solution, in the sense that beyond a point you can no longer predict what will happen to the system, how it will evolve. Point is, you have an identical system of okay, fine, okay, all right, but not when we want it. Okay, fine. Okay, each of these actually started from the same initial condition. They were identical, right? But as has apparently happened, the motion of each of these are different. It's entirely different right now, right? So it's a three-body problem, and there's been a very slight perturbation in the initial condition, which has led to a very different dynamical behavior of the system. This is what we are interested in, things like this that we're interested in when we talk of dynamics of the system. It's a three-body problem. You wouldn't have this strange behavior if you had a two-body problem, of course. Right. So, right. So the other development in nonlinear dynamics following Poincaré was much later, earlier in the last century, when Lorentz, who was interested in describing climatic systems, made a model of these atmospheric rolls that you see here. These are clouds, also known as cloud streets. You have these long furrows formed by convective motion in the atmosphere due to clouds. The question was, how would you describe these things? So what he did was he set up a set of three coupled differential equations, and what he discovered was that if you have even slight perturbations in this, it leads to a very chaotic system. A slight perturbation in the initial conditions. Suppose x was 0.001 when you started off with the system, and then you again look at the same system with a slight perturbation, in the sense x is now 0.001, and maybe in the 15th or 16th decimal place you add some number. That will cause a drastic change in the behavior of the entire system. That is a characteristic of a chaotic system, which is a nonlinear system. So what he did, the equations that he set up for this cloud rolls have since become famous since then. And these Lorentz equation, if you plot them in 3 dimensions, these lead to this famous Lorentz attractor figure. So it's a butterfly-shaped set of points, and this kind of the poster child for chaotic systems. Essentially, it looks very beautiful, especially when you rotate it. So the point is, however well you write your equations, if you claim that you can predict the weather, you are making a very tall claim, because any small change in the initial conditions is going to lead to total unpredictability in the system. Okay? So this is what they say when they talk of the butterfly effect, which you would have heard of off and on. The claim is that if a butterfly flutters its wing in the Amazon, the weather in the South China Sea is affected, things like that. Okay? That's what they mean. Slight change in initial condition and the system goes haywire. Okay? So this is what we mean when we talk of chaos. Not all nonlinear systems are chaotic, but all chaotic systems are nonlinear. So when you talk of dynamical systems in general, what we do is we describe them by a set of ordinary differential equations or partial differential equations, or if you're talking of a discrete systems, iterated maps. And what you do is to look, the general way of looking at things is you see how stable the system is. And you can have a linear stability analysis or a nonlinear stability analysis. Simplest way to go about is to linearize the fixed points. So you write down the linear stability matrix, find the eigenvalues, and that will tell you about the stability of the system. So you could have various kinds of fixed points or equilibrium points. You could have a node, means the system evolves towards one point from outside. You could have a saddle in the sense that the system goes towards this fixed point from one end but moves away from it in another direction. Or you could have a limit cycle, you could have a closed form solution. Or you could have a center, means for example if you were to look at a simple pendulum and you were to plot the energy, plot the momentum versus the position, you would get ellipses for different energies. Or you could have a focus, it spirals inwards. If it's a stable focus, the system spirals towards your fixed point. Otherwise, if it's unstable, it moves outwards. So various things are there. So when you plot a phase portrait, essentially the velocity versus the coordinate, you can see various possible equilibrium points. For example, a stable node, which is this black point, since the system evolves towards it with time, or an unstable node, the system moves away from it with time, things like that. Or you could have saddles, things this place here, moving towards it from this direction, moving away from it in these directions. Likewise here. These are just the various ways of describing a nonlinear system. I will not be using these, of course, in today's talk. This is just to give you a general idea of how things are treated. So, as of course the parameters controlling the system are varied, the stability of the system will change. And when you say you have a bifurcation in the system, what's actually happening is you have a drastic change in the stability at certain critical value of the parameters. So typically when you plot a bifurcation diagram, you have something known as the control parameter on the x-axis and the dynamical variable on the y-axis. So depending upon the value of your control parameter, you can obtain a bifurcation diagram which will tell you what possible ways the system could evolve. In another branch of, so all this is essentially applied maths. So when you're in physics, when you're working condensed matter physics and you talk of phase transitions, that also is essentially a bifurcation. It's a change from one state of the system to another at a certain parameter value. So when we talk of a bifurcation, essentially it talks of changes in the equilibrium, the number of fixed points that are there in the system, the dynamics. A well-behaved system could suddenly become chaotic, and so on and so forth. Now, all these vary as the control parameter is varied. And of course, there are various kinds of bifurcations and instabilities. We will not go into that today. Right, so one standard example that's always given when you talk of bifurcations and instabilities is the Tacoma bridge disaster in 1940. And more recently, we had a new example given to us when the Millennium Bridge collapsed on day one over the river Thames. So what happens is when you are describing such a system, when a person builds a bridge, an engineer builds a bridge, he's supposed to have taken into account all modes of excitation to the structure. Of course, if you are overconfident, you think you have done everything, then you are in deep trouble, as the Tacoma bridge disaster kind of exemplified. I'll just show you. It's a 2-second video or something, so you'll just have to pay attention. You'll see a tar laid bridge over this kind of structure, and there was a wind on that particular day, and you can see the whole bridge warping and oscillating. It's just the standard example that people love to show. So yeah, this is a bridge, a steel and concrete bridge. Okay, I'll just show it again. Okay, you can see the whole thing oscillating, right? This happened because they hadn't taken into account the oscillations in the structure. Okay, and if you want to see it crash, there it goes. Okay, so that's what happened eventually. A car also, that's one more movie which shows a man rescuing a dog from a car, things like that, but you get the general idea. The bridge collapsed. So these are the things that a study of instabilities, bifurcations, and dynamical systems would allow you to avoid by knowing how to actually construct the system. Evidently, they have colored it since, I don't know. Okay, so I talked of dynamical systems and soft matter. So just so that there's no doubt left about what I mean by soft matter, essentially soft matter is soft matter. We talk of polymers, colloids, surfactants, liquid crystals, things which are not exactly crystalline. Like, okay, and they are not crystalline, they are not liquid, so they are kind of malleable. So many things that we see all around us, plastics, textiles, rubber, living tissue, gels, creams, all of these fall into this category of soft matter. And soft matter materials generally have a characteristic property that most of them are viscoelastic, in the sense that they are both viscous as well as elastic. And what do I mean by that? When we talk of viscous materials, for example honey or other liquids like that, these materials resist shear flow. That is, when you have a force like this, a shear, they resist it, and this happens linearly with time. There's no nonlinear relation between the force applied and the deformation. Moreover, the other thing that we talked of, when you say viscoelasticity, we're taking care of the viscous part. When you talk of elasticity, in this case, the strain to a force is instantaneous essentially, and it jumps back to its earlier configuration once the force is removed. So viscoelastic materials have a bit of both. Depending upon the rate at which deformation, when force is applied, if it's slowly deformed, it behaves like this. If you apply force rapidly, rapid deformation, it fractures. So it falls in between this. It's both viscous and elastic, but not quite either of them by themselves. So there are some nice properties of some soft matter fluids, for example polymeric fluids. And polymeric fluids, because the deformations are not quite normal that you see classically, they're called non-Newtonian fluids. For a standard day-to-day liquid like water, if you remove a siphon from the liquid, water will not flow through it. On the other hand, for a polymeric fluid, if you have a siphon in the liquid and then you remove it, there's a gap here, the liquid will continue to flow through it because the axial strains are much longer in this direction. So once you start the motion, it keeps going. Okay, so those are non-Newtonian fluids. All of these are soft matter fluids. I will not be talking of polymers, of course, but this is to give you a general idea of the field. And finally, just an idea of length scales. When we talk of bubbles and nanotubulation, it's in the nanometer scale, micrometer scale. So how do you quantify these? Okay. For example, a single hair has a diameter of 100 micrometers, 100,000 nanometers, right? If you look at a red blood cell on this hair, the diameter of that alone is around 6,000 nanometers. And the DNA, for example, has a diameter or radius of cross section of 3 by 2 nanometers. Right? So just to give you an idea of give you a feel for the numbers. So when you talk of blood vessels, it depends upon where the blood vessel is located. It could be in millimeters or a few micrometers. It depends. Or it can even go down to 30 nanometers or so, depending upon where you are in the blood, in the human body. So the first part of the talk, we're going to talk about charge bubbles. What will happen when you excite them? Okay. So essentially, you have a pressure wave coming, an acoustic wave, which is in the ultrasonic range. Ultrasonic means anything about 20 kilohertz. And then we apply a standing pressure wave to a gas bubble in a liquid. It gets excited. Okay. And depending upon what regime of the pressure wave you are in at a given instant, it either expands, the bubble expands or contracts, and you see various phenomena. It could burst, it could implode, things like that. And that's what we are interested in describing. And this has practical applications in industrial applications, because when a bubble bursts, when it implodes, the energy release is enormous, and it causes this kind of damage, which is known as cavitation damage. So we'll see. So the idea is to, in general, describe what's happening. So when you have bubbles all around in daily life, as you can see, when you have boiling stuff, it's used in inkjet printing, in bubble chambers when you want to detect high energy particles, or also generated by breaking waves, which are sinks for atmospheric carbon dioxide, various things. Practical applications include sonoluminescence, that is when light is emitted when you excite a bubble. Ultrasonic cleaning, as you can see, various in drug delivery. You can cause a capsule to implode by applying an ultrasonic wave to have local delivery of drugs at some point of the body. Various other possibilities, and there's ultrasonic scans, of course. Supercavitation, where you can envelop an object in a huge bubble that will reduce drag. So you have actually practical applications. As usual, when the war machines are in the forefront of development of science, in the sense, one practical application people have found immediately is to make a supercavitating torpedo known as the Shkval, Russian torpedo. When it moves at a high speed so that it's enveloped by a bubble. So there's no friction in its motion. And also you have one of these pistols, I think Glock or something, they have a bullet which is a supercavitating bullet essentially. So we excel in these kind of stuff. Anyway. Bubbles also, you see them all around in daily life. When you hear rainfall, why do you hear the nice sound of rain? It's because of bubbles which are imploding and pattering down, right? And this can have practical applications. If you want to measure rainfall in the middle of the ocean, how will you do it? You can't keep a water gauge there, right? Rain gauge. So one thing to do is you can use an acoustic rain gauge, and because depending upon the diameter of the bubbles that implode due to intensity of rainfall that's coming, they'll have a characteristic frequency. So you can just have sound detector, and you can measure what's the spectrum of the rainfall essentially, let's say that. Okay, what are the frequencies of sound being generated? So that will give you a measure of the actual rainfall occurring. Okay. Right. Okay. Right. So normally when we want to form a bubble in water, what you would do is you would boil it, you heat up the water. And when you do that, small bubbles start to form and the water starts to boil. So that's one way of forming bubbles by heating, right? When you heat it, what happens is the liquid vapor pressure, that is the amount of vapor form that is in coexistence along with the liquid that's coming from the earth, coming from the liquid you're heating up. When you heat it, the liquid vapor pressure is raised to match the atmospheric pressure, and bubbles are formed, it releases into the atmosphere. That's one way of doing it. The other way of doing it is to lower the local liquid pressure so that it matches a point that's below the liquid's vapor pressure, in which case again bubble formation takes place. If you want to boil water at room temperature, this is what you would do. Lower the liquid vapor pressure. It's obvious you would be knowing about it, but when you see it, it's a different thing. So I think it is this. One second.
Water boils when it is heated, but water can also boil at room temperature. In this glass venturi, water is flowing from left to right. According to Bernoulli's integral, where the velocity is increased, the pressure is decreased. When we increase the flow rate, the water in the throat, where the pressure is lowest, begins to boil.
Right, so essentially what he has done is, by increasing the flow rate by Bernoulli's principle, increase flow of a liquid decreases the local pressure. And the local pressure has been lowered so far below the vapor pressure that bubbles formation has taken place. Essentially it's boiling at room temperature. This is what is being meant. And also this can also happen when you have a rapidly rotating propeller. You have low pressure regions being formed within the liquid, and then bubble formation takes place, and bubble implosion can take place. And this whole field of bubble dynamics was first started by Lord Rayleigh when he was asked to look at the question of damage to the propellers of the Royal Navy's ships. Okay, that was how this whole field started. So there are a couple of more videos which I'll show later because we'll get to it later on. So essentially what we see is that for cavitation to occur, you need to have some kind of impurity where you can first initiate bubble formation to occur, to start. So a speck of impurity is enough. Then any small pre-existing bubble, they'll start to grow larger and larger depending upon the pressure. And above a particular threshold pressure, which is known as the Blake threshold, the bubble expansion takes place violently. And another corresponding pressure threshold, just like it expands violently, they have a corresponding pressure threshold where violent collapse takes place, and that's known as the upper transient pressure threshold. And this is this one I think I should show you. This is very relevant when it comes to the phenomena known as sonoluminescence. Okay, so all right, again I'll come to it a bit later. So again, as you are seeing, cavitation bubbles form when vapor gases which are diffusing into the cavity from the surrounding medium. It's not a perfect vacuum, but you have a relatively low gas pressure. Collapse can take place due to high pressure of the surrounding medium. So this kind of thing, it expands and then it collapses. When it collapses, you have a water jet kind of thing forming inside it. Okay? Pressure and temperature of the vapor within the bubble will increase drastically to several thousands of degrees. So this is in a gas bubble in a beaker which is sitting on your table, several thousands of degrees at a point within that. Okay? And along with this heating effect, you can also have a significant amount of energy that's released, like a acoustic shock wave, a sound wave, and visible light. Yeah. True. So the ideal case, it is uniform, of course, but in that case you talk about what is known as radial breathing mode. So everything is radial, but because of local non-uniformities in pressure gradients, you have deformation taking place. But our treatment is the, sorry? Outer space, okay, here, alright, fine. Outer space, it will be probably radial symmetry will be there probably. Probably is. So, so as I said, it all started with the work of Lord Rayleigh, and it was subsequently modified by two people, Plessey and Prosperity. And all these things talk of uncharged bubbles. And like I told you just now, when you talk of light being generated, that's a phenomenon of sonoluminescence. You have ultrasound acting on a gas bubble, and you have a standing wave, pressure wave due to the acoustic wave. The bubble gets compressed and light gets generated. You see this blue speck here? Seems very insignificant, but that's your sonoluminescing bubble. It's a xenon-filled gas and it's a water-filled cylinder. And that's one very beautiful video of this phenomena by the Putterman group in UCLA. This is it. It's a gas bubble. Just keep watching. There. You see that? That flash of light is sonoluminescence. Okay. So expanding, contracting due to the acoustic ultrasonic wave being inserted on it, and it's being compressed so that the gas inside is ionized, light is being generated. Okay. So this was essentially the, you might all remember the talk of cold fusion and all, of getting limitless energy from your tabletop system. It was all due to this kind of, nothing came out of it, but that was the sonoluminescence was the motivator behind it. No, eventually it will leak out. All the gas will leak out. So, and you are giving force. You mean this system, right? Not really, because you are providing energy in the form of a pressure wave. So, it depends upon the amplitude of your pressure wave. Accordingly, the bubble. See, depending upon what frequency you are pushing it with, what amplitude of the pressure wave is, the behavior of the bubble changes drastically. So this is typically 180 kilohertz or something, a few microns size, 1.12 atmospheres. It lasts so long as the bubble doesn't diffuse out of the bubble, the gas doesn't diffuse out of the bubble. So this is what you see actually. This is a plot of the radius of the bubble. The red one is the plot of the radius of the bubble as a function of time. The green line is your pressure wave, acoustic pressure wave. So obviously it will have, it's a pressure wave obviously, so it will have a negative part, a positive part. When you have a negative pressure, then the bubble expands, okay, reaches a maximum. Then comes collapse. It collapses to its minimum point here, which is marked by a spot. But then because inertia is still there, these are what are known as after bounces. Collapses, but because of inertia it bounces a little bit radially. Okay. So it's at this point, this spike that you see, that light is emitted at this point, and corresponding to that you have a shock wave. So you see a spike in the pressure wave. Right, and this light flash lasts for picoseconds, and this can occur only above the Blake threshold. Blake threshold, you will remember, is the pressure required for maximum expansion.
What about the frequency of light? Is it like the Sonic frequency or the frequency of material?
It's in picoseconds, lasts for picoseconds, and it's in, I think it's in nanoseconds time. So nanosecond inverse, I think. It's roughly terahertz, I think. No, you can see a visual spectrum. It also has an ultraviolet component, as far as I recall. Also, typically when you have an ideal gas in the bubble, you get the best effects. So not so nice when you have just air inside. And as I told you earlier, other applications include sonochemistry. When you want to have perfect reaction, what you do is you apply a sonic wave to it, the material crumbles, and then you have a nice reaction. You can expect it. Surface area increases of the material. It depends. I'll just show you. Means it Rayleigh collapse by itself is just a collapse of an ideal void. Okay, no gas, nothing. So Rayleigh collapse doesn't really tell you anything. Okay, but I'll come to it. I'll just show you a few. Yes, roughly. Right. So our work actually, for some strange reason, is the first ever calculation of pressure and charge thresholds for imploring charge bubbles, micro bubbles in fluids. The only other work that we found in the literature who have done something on charges, and I'll tell you in a minute why I'm talking of a charge bubble. The only other people are these guys, these 7 people. It all started with Mactaggart even before Rayleigh, 1914. We talked of electrification of liquid gas surfaces, so it's not quite what we are doing, but that was the closest we could see. And subsequently, IIT did some good work on that, Akulichev as well. And more recently, Grigoriev and Zharov talk of the stability of a charge bubble in a dielectric fluid, except that they make some approximations which wipe out the initial assumptions. So I wouldn't consider this as a valid study, but anyway. The reason why we are surprised that more people didn't work on this is because when you have a gas bubble in a liquid, any gas bubble in a standard beaker of water, because of dissociation of ions, you have migration of electric ions from the surrounding liquids to the bubble. So to talk of a neutral gas bubble is actually physically not realistic. All gas bubbles that you see in a liquid do have a negative charge sticking to them, at least when they are in water. And that's of course a lot of discussion about where it's coming from. People say it's due to trace impurities in the liquid. Others say they are because of dissociated free ions. Anyway, you have some talk. The original Rayleigh equation, which talk of a bubble, a void in a liquid, had only these 2 terms. I'll just show you. R dot R times R dot R double dot equal to 3 by 2 minus 3 by 2 R dot square. This was the two terms. That was the original Rayleigh equation. Subsequent amendment by Plessey and Prosperity included all these terms, not these. All these other terms, but not these. What we did was include a charge, so obviously the pressure profile changes, so we had to include this term, and it comes in. It also makes its way into the R dot term, obviously, because it's all related. So the presence of charge essentially modifies the surface tension of the bubble and reduces its effective value to this quantity. Sigma is the surface tension in the absence of charge, Q is the charge present on the bubble, R0 is its ambient radius, epsilon of course is the dielectric constant. So this is what you see when you plot and solve these equations. So these are plots of radius versus time, and these are phase portraits, R dot versus R, velocity versus radius. Okay. Depending upon whether the bubble is charged, which is in blue, or not, you will see variations in this, or in all of these. These are at rather low pressures, 100 kilopascals and all, so you don't see such a drastic difference between the two. One place where you do see a big difference is in the temperature. In the case of a charged bubble, the difference is much larger actually compared to an uncharged case. Okay. So all these plots, when you look at these are after bounces, the bubble expands, contracts its minimum radius and so on. And these are phase portraits. These could be chaotic, non-chaotic, things like that. So it's very dependent upon the pressure at which you are driving the system. Right. So as I just mentioned, at higher frequencies the influence of charge is much more pronounced. This is the phase portrait R dot versus R when you have zero charge, standard bubble. So you see the smeared, all these regions in the phase space can be occupied by the bubble. However, if you add a small charge, 4.25 to 10 to the power minus 14, very tiny amount, then the phase space miraculously reduces to this thing. Okay. Only all these regions which the bubble could earlier be in are no longer accessible now. Also, if you look at the power spectrum, you do a Fourier analysis of the frequency, you see the power spectrum. You see that in the presence of charge, certain oscillatory modes are absent. Q equal to 0 corresponds to the blue lines here. So you have blue here, all over here, everywhere. When you add charge, the red line comes here. You have a few subharmonics showing up here, but it's absent in certain other frequencies. So it reduces the regime of oscillations that's possible. The other things that are important is how quickly does the bubble collapse. So is the bubble collapsing adiabatically, that is without transfer of heat, or isothermally at constant temperature? And that has a big effect on the equation of state of the gas within the bubble. Right, so if heat transfer is fast enough with respect to the speed of sound, then it means that you can say the bubble is at constant temperature essentially. The bubble motion is even faster, pressure is described by an adiabatic equation of state. So using our results, we are able to obtain various relations between the radius of the bubble and the frequency at which you are exciting the bubble. And you could see, but one important thing to take into account was the bubble cannot indefinitely contract, because obviously you have beyond atomic scales you can't have any contraction. So we are essentially limiting our system to the van der Waals radius of the gas. That is the smallest atomic interaction between atoms in the material, below which you can't actually have a contraction, obviously. But the nice thing is you're able to get analytical expressions for all of these about the radial expansion of the bubble and how quickly it could, to what extent it could expand. Sorry, one second. Where is the, oh, this thing, sorry, this is Cp by Cv, ratio of specific heats. So that's what comes out of the, when you have an adiabatic equation of state, it comes to 5 by 3. So in the adiabatic equation of state, PV raised to gamma is a constant. So otherwise it's PV equal to nRT, gas law. So I told you about the Blake threshold, which is the pressure above which the bubble expands violently, right? Now, thus far in the literature, there has been no way of identifying from one plot where the Blake threshold is and the upper transient threshold is. Upper transient threshold is where bubble collapse takes place violently. So in things like sonoluminescence, you want to know when the bubble is going to collapse, right? So we introduced a quantity zeta, which was essentially this quantity, the expansion divided by the compression dimensions of the bubble, and fortuitously it gave us this nice curve. This part here, this peak here, and this bottom here, this nadir here, are essentially the thresholds. This corresponds to the, and this is a plot of again the same quantity here versus pressure, except that now I included the velocity of oscillation as well. Here you can see it has come up and then it has slowed down. So it has gone up to its maximal radius. So this is your Blake threshold. Then zeta comes down dramatically, which means this has increased, right? So here you have collapse occurring. This is the upper transient threshold. And then velocity shoots up once you have passed the upper transient threshold. So the interesting thing is when you have charge on this bubble, this whole system shifts to the left, and when you increase the frequency, this arm moves down. So you have a very good control about how you can predict what will happen for a given frequency or a given charge, how the bubble will oscillate, where its Blake threshold or its upper transient threshold is. It's very important when you're talking of considering cavitating phenomena in looking at machinery, or even in the case of medical diagnostics. When you have ultrasonic scans, the body is full of soft matter and you have ions, charge bubbles in there. How do you know the scan is perfectly safe for you, right? So this is one way where you can modulate the amplitude of your scan, pressure amplitude, so that you are in a safe regime. So again, we are able to predict the minimum charge required for the bubble to move with a given velocity. We are able to plot an isovelocity curve. So depending upon what velocity you want collapse to take place, you can tune your charge. Similarly, beyond a particular, for the bubble to reach a minimum radius, you can't have anything more than a maximal permissible charge. So you can't put n number of charges and say that you can indefinitely increase the charge on a bubble. That's not possible. You find that you have a physical limit to what is permitted. Again, I mentioned bifurcation diagrams earlier. You can use both the frequency as well as charge as control parameters. So essentially for this frequency, the maximal radius of a bubble can be all of these, any of these. That's what this plot shows. That's what a bifurcation diagram is. So when you change the control parameter, it moves. Okay. This kind of bubble, okay, this is also a bubble, but this kind of period doubling that you see, the split in the plot, this has occurred because you introduced a non-zero charge onto the system. At the same frequency here, there was nothing happening, but here when you introduce a charge, period doubling has taken place.
Behavior, does it depend upon the polarity of the charge?
Not really, because it comes as q square. In the equation comes as q square. Of course, we put a negative charge just to be consistent with what is seen, but it won't matter. Yeah. Wait, there it's in, you have something called the mechanical index, which is the ratio of the pressure amplitude to the square root of the frequency. That's supposed to define the safe regime. So there goes up to several megahertz frequency. Pressure amplitude is also 1.2 to 2 atmospheric pressures, I think. I'm not sure about this, I'll have to look it up. But the way they do it is depending upon the frequency, they tune the pressure amplitude so that it's in a safe mechanical index value. That's how they do it. You don't know. Seriously, because so far, what you see when you are using it, you come out fine, right? So all is well with the world. But what's actually happening inside, you don't know. So this has implications specifically when you are doing ultrascans to children and all, where the tissue is much more delicate. This will have implications there. So the problem is to get people interested in making measurements. Okay, the one issue here is it's charge all right, but how do you measure the charge, right? That's an issue. So no, what I'm saying is for all practical purposes, all these years it has seemed safe. Let us put it that way. So it has worked so far. So evidently something is okay, but that doesn't mean nothing. Everything is okay, right? So right. So depending upon the quantum of charge that you have, the range of the bubble radius will also vary, right? So that's what we are able to predict where you are using this bifurcation diagram. These are just representative plots. It will vary with the bubble dimension, frequency, pressure amplitudes, but you can calculate it. That's a good thing without tuning parameters. Of course, the other thing is, if you are above a threshold or below, the behavior changes drastically, because if you look at this, this is the maximum velocity of the bubble oscillation as a function of frequency. For certain values, okay, this is for q equal to 0 charge, okay, q equal to 0. These violet guys are for 0 charge but below the pressure threshold. Okay, so above the pressure threshold, velocity decreases with increasing frequency. Below the pressure threshold, velocity increases with increasing frequency. So there's a distinct two classes of behavior depending on which pressure regime you are operating in. Similarly, if you looked at the radius as a function of the amplitude, pressure amplitude, the maximal radius, depending upon whether the bubble is charged or not. So in this case, I'm showing this for a radius bubble of 2 micrometers at a driving frequency of 25 kilohertz. The solid curve corresponds to the charged bubble, 0.14 picocoulombs. The other one is the uncharged one. There's a shift in the possible values that the bubble can attain, maximal and minimal radius. So that's a very distinct behavior when charge is introduced into the system. Again here, dependence of the radius upon the pressure amplitude. The green one corresponds to 1.42 atmospheric pressures, and these are with increasing pressure amplitude. This is 1.45 and this is 1.43. Apparently small change, but drastic difference in behavior. And in this case, you have pressure is kept constant at 1.42 amplitude, pressure P0, atmospheric pressure, uncharged and increasing charges, right? So that's a distinct change. Small amount of charge drastically changes the behavior. Right, so that essentially ends the first part of what I was going to say about bubbles. The other part I'll briefly go through quickly is on nanotubulation, vesicular nanotubulation. And this is essentially what happens when you deform a vesicle. A vesicle is essentially a phospholipid, it's a bag made of phospholipids, phospholipid membrane, which could have a single wall, multi-wall, that kind of thing. And it's essentially present all over your body. In the cell, if you want to transport chemicals from one part of the cell to the other or between cells, these are the guys who are actually doing the transport. Bags, okay. Water carriers essentially. So the question is, if you were to pull at this, how does it behave? Okay. So in the lab, what has been done by several people is, they put this multilamellar vesicle, this phospholipid bag, which is of the order of a few micrometers, 10 to 100 micrometers in diameter. They stick it to a glass slide, and by means of an AFM tip, they pull at it at constant velocity, and then they measure the force extension curve. So if it's a nice, well-behaved curve, you are going to get a smooth curve, but that's not what is seen. So this is just a schematic of what is being done experimentally, and this is the diagram I use for modeling it, but not really important right now. Before I go ahead, I'll just again tell you what a vesicle is. For example, in neurons across the synapse, what is it that transports the neurotransmitters across the synapse? It's these vesicles. So these vesicles come over here, come over to the synapse, they break open, and the neurotransmitters are released. These are chemical, it's a chemical synapse in this case. And these guys, this purple kind of thing, forming the wall of the vesicle, is made up of these phospholipid molecules, which are of the order of a few nanometers in length. They have a polar head and a polar hydrophilic head group, non-polar tail, and when you pull at it, these are the guys which are causing some interesting behavior that is seen experimentally. Right, what is seen experimentally? These are the experimental plots, force versus length. If you have a lipid reservoir behind this vesicle, this is a vesicle which is attached to a glass pipette. You have a lipid reservoir in the back, you're pulling at it, you get this force extension curve. It rises up, falls with a jerk, then you have these jerky things, but it's essentially a plateau. Or if you don't have a reservoir, you're just pulling at it, you get these upwardly rising curves. Question is, why do you get these? So our aim was to try and explain the sharp rise in magnitude here, the drop, this plateau-like behavior, or the steeply rising curves, and why do you see these serrations? And various people had worked on this earlier. Group at Boston University in British Columbia, Goldstein's group in Arizona and Cambridge, great many people, but none of them had actually addressed the dynamics. They looked at steady state solutions, they didn't look at the dynamics. By dynamics I mean the time evolution of the system, which is necessary to explain these curves. So one one reason was many of them dismissed these curves as being, these serrations as being an effect of noise, thermal noise. You have jerky things happening, so it will anyway come. That's what they assumed without looking at it. So what we did was we modeled this by a set of block and spring, well, sort of block and spring systems. We had to take into account various things like the curvature of, okay, this was the body of the vesicle. As each of these phospholipid molecules were pulled, you remember it has a polar head and a tail. So when it's being pulled, you're going to have a brush kind of effect across it. And this is a steep curvature, so you have to include local geometry. You have to include curvature term here. Apart from the elastic term, viscoelastic term, as well as other effects, right? So you had a neck formation which takes place when the vesicle is pulled out. So you have to take into account energy needed to form the neck. Then the curvature term right here at the base of the neck. Then when the initial ideal spherical vesicle gets deformed by a force into an ellipsoid, curvature energy changes. Then when the ellipsoid gets pulled out into a cylinder, again the curvature energy changes. You have to take into account all of these things. Having done that, we got these curves, okay, which was very nice theory. Okay, again you will say it doesn't go upward so much, the curve isn't there. That's because just look at the numbers. This is up to around 3 micrometers, which is right very near the start of this curve. So if you were to magnify this, hopefully you will get something like this. But it captures the two behaviors. At constant surface tension, you get a plateau. Non-constant surface tension, you get a curve. And it behaves exactly as seen experimentally. Increase the pulling velocity, the red curve, they fall below this, here. Increase it still further, the amplitude of oscillations kind of smoothen out and they go to the top, exactly as seen experimentally. So this is, even though I say so myself, it's a really nice theory because I'm quite pleased with it. So what we see here is the overshoot here, that's determined by the curvature term at the base of the neck. When you're pulling, each single molecule is coming out from the main vesicular body. This here, the serrations are determined by the brushing of each phospholipid molecule with each other. Right. This point here corresponds to the sphere to ellipsoid deformation. When you see this, what you see here is the sphere to ellipsoid deformation. And the plateau is due to the tube formation. When you have tube formation, you have constant curvature energy. So that's this plateau. So we are able to explain all these terms: initial serrations, sharp rise in magnitude, drop, plateau-like behavior accompanied with serrations, everything essentially. We solved the equation. Yeah, yeah. So it's not a molecular dynamic simulation. It's just a solution. Yeah. Oh, you mean this? Now I'll just show you again the equation that we have. We don't. It just comes because you have a damping term here, which might or might not, depending upon which system you are treating it. You have this, this thing is actually important. This is responsible for the serrations. This corresponds to the frictional term in the system. When you're pulling at it, this is the friction term. So this alone corresponds for the serrations. All the other behaviors which matches with experiments come from the curvature terms, the damping term, the various other elastic terms. Only the serrations come from these guys, this guy. Okay. So there is no sinusoidal term. So this is because of stick slip. So when you have something sticking, there's enough force that you overcome the local slip. But then the next phospholipid molecule shows up. Then again you have to put some pressure. So again you have a peak. So up and down, up and down. And in between you have inertia. The object is already moving with some velocity. So that's why they are not identical serrations. Okay, the reason why it's practically important is because suppose you have trace amounts of chemicals and you want to actually find out what all is there. If you want to actually identify all the chemicals in a spec of sample that you have, You can't put it in a test tube, obviously. You need a very tiny container. So for that, these guys are ideal candidates. Make vesicles and nanotube structures out of these. These have actually been formed. There's a group in Sweden, Orva research group. These guys have made these micro reactors for trace identification of trace chemicals. So this has got practical implications. So which is why we looked into it. It's good to know how to make it and what all factors play a role in nanotubulation. Okay, finally, one last topic just for this, and I'm done with it, one sheet. We also were able to do, this is a third topic essentially. Microtubules, you might know, are essentially present in all living organisms, present all over. They are present in the cytoplasm, in the cell. They form the cytoskeleton. You have plants growing. They form the structure around which the growth of plant cells take place. So they are all over the place. They are also, even in you and me, they form the scaffolding over which you have transport of vesicles from one part of the cell to the other. So these guys essentially consist of two proteins, the alpha and beta tubulin. So you can see these two colors. And as you can see, they are arranged helically around a hollow core, roughly 10 to 25 nanometers in diameter, roughly 10 micrometers long, 10 to 50 micrometers long actually, each of these. So the question is, we are interested in seeing whether a theory of ours which we had done long back about the effect of electric fields on copolymers. A copolymer is a polymer made of two compounds A, B. We have a repeat compound A, B, a chain. That's a copolymer. It's called a block copolymer. The presence of an electric field, if these two compounds have, these two molecules have different dielectric constants, they preferentially orient themselves. So it's like what is known as the Friedrich transition in liquid crystals. You apply an electric field or a magnetic field across a cell with liquid crystals. Beyond the critical threshold, what was initially aligned like this flips. So this has practical technological applications. In a sense, if you want to make small structures, small vertical structures in the nanolithography and all, how do you get these vertical structures? You align them with an electric field. You align these polymers with an electric field, apply acetic acid and leach out the polymer, and then put in your gold nanotube or whatever you want to. You get these wires. Okay. Anyway, that was that. So we thought that that could be, I could apply it to this structure, because there's a question mark about the actual length of these tubulins. One thing that is known is that they are affected by electric fields, which was why the thought came in. So if they are applied by electric fields, I assume that they should also obey the law that we found earlier in a different context, of course, that the persistence length of the two components should be greater than a certain quantity. F is the composition, how much percentage of composition is there. Persistence length, incidentally, is if you have, that's the difference between, normally in physics when you talk of objects, they are point objects. When you talk of polymers, they are chains, strings. So persistence length is that tangent, that length of tangent along the string where there's no, the correlation is still there. Beyond that thing, the correlation breaks between the two. So it's a kind of stiffness, measure of the stiffness. So we made the following prediction, seeing that they will be applied by electric fields. Using this expression, we predicted that the dielectric constants should be different. And lo and behold, if you look at the experimental data, they are different. And we also made a prediction on the persistence length of the two, because there's a question mark about the actual values of the alpha and beta tubulin persistence length. From our theory, we predicted it should be roughly 1.85. It's the back of the envelope calculation. The actual value is actually 1.35. So not too bad, but not good enough. So this is one more place where we are able to apply theory from generic different framework to something in living matter. Okay. So I'll stop here. Thanks.